Hi everyone, we're the Rainfall group. I'm Jess.
I'm Erin.
I'm Diana.
My name's Adam.
I'm Seth.
I'm Lane.
And we're going to be exploring what we did for our project today.
Oh, okay. Alright, so to give you guys a brief summary of the data that we used, we had daily rainfall data from 535 weather stations located throughout the Gulf Coast area, and we have daily data from the year 1949 to 2017. And the data was provided by Karen Comfort from NC State University. The general question that we tried to answer was how to describe extreme maximum rainfall data. And we started off with making two different approaches doing extreme value analysis. And one of the approach was block maximum approach. To give you an example of how this approach works, we chose like one station, specific station, the Hobby Airport station, and we split the data into blocks, which was corresponding to a year in this case, and we found the maximum rainfall, daily rainfall of each year, and then fit the generalized extreme value distribution to the maximum rainfall events. And the second approach.
And the second approach we use is the peak over threshold approach. And our motivation to use this approach is that we want to include more data observations in our subset in order to improve our estimations of the extreme values. And take the Houston Hobby Airport as an example, we will exactly got almost 1,300 observations in our data set instead of 69. And there are majorly two steps in this procedure. The first one is we want to choose a value to function as the threshold. And the second one is that we want to generalize the Pareto distribution to rainfall events including and above the chosen threshold. But actually it is quite difficult to choose a good, or how to say, the best threshold to each individual location. So in our research, we simply to choose the 95th percentile for each location as their own threshold. And the time series plot here is quite the same as what we got from the block maximum one. But as we can see, there are more dots shown in this plot. This is simply because that we choose more data observations here. And also there is another difference is the red line. This red line is follow the generalized Pareto distribution.
Here we are looking at QQ plots. What we did is we fit the distributions, a generalized Pareto distribution and a generalized extreme value distribution, to our empirical data. That gives us fitted values for those distributions, and then we obviously have the empirical data. What we'll do is we'll sort both the empirical data and the fitted values, and then you'll see on the x-axis we have the sorted fitted values, and on the y-axis we have the empirical data, and we're just lining them up. If you have an identity function, something like y equals x, those values are fitting pretty ideally. This is sort of a crude way to analyze if we fitted it well. And another issue with these graphics is that the generalized Pareto distribution, since it's taking values over a certain threshold, it has a lot more data than the generalized extreme value distributions. The GVD fitted values, we have about 69 of them for our 69 years of rainfall events. As opposed to the threshold approach, we have somewhere on the order of thousands. So it's a little difficult to compare these two QQ plots, especially when you look on the one on the left. It looks like it's fitting really well, but there's also so many more points there. Another way that we can talk about or compare between these two different approaches, GPD and GEVD, is to look at return levels. Return levels are, after so-and-so years, say 100 years, what would we expect the rainfall event to be? Like, how much rain after 100 years would be classified as an extreme event. Here we're looking at the different return levels for the threshold approach and the block approach. We've plotted confidence intervals. Both of them are returning return levels of about 12 with confidence intervals that do include some observations that we've seen. In the end, we chose to use the block Maxima approach. This is fitting a generalized extreme value distribution to the empirical data. One reason we are doing this, as Lynn said, is it's actually very difficult to implement the threshold approach. It would take a lot of work to go into each station and pick an individualized threshold for that. Another reason that we're doing this is because the reason you would use a generalized Pareto distribution, like the theory behind it, says that the threshold should be converging to infinity. In our case, the thresholds are normally around 1 to 2. I don't know about you, but I don't think that's getting close to infinity. So I think a big assumption is being violated here, so that's another reason why we chose the GVD method.
So here we're choosing to use the return level to quantify the extremeness of the events. The application of this is when you're like building a bridge, you want to know what's going to be the largest rainfall event in the next 100 years. So if we're going to compute the return level with a return period of 100, that's what we're going to get. So the approach we're taking here is we're using this GEV, that it stands for General Extreme Value Distribution, and the data. So what we are doing here is we're trying to compute the estimator for all three of them. This is the location parameter, is sort of like the center of the data. And this one would be the scale parameter, which is kind of like the span of the entire data. This is the shape parameter. We actually didn't see a real word application to this, so it's really just kind of a parameter for this model. So on this slide, you will see what's on this slide is the location parameter. So if we have a stationary time series, the location parameter will be the constant for each location. If it's a non-stationary parameter, it will be a simple linear function that's kind of like mu equals to alpha plus beta times t. So it's a function with respect to years. So here it's just a location of a stationary plot. On the next slide, you will see the scale parameter for the stationary time series. So what we ended up doing is we actually made an animation of a stationary time series that kind of shows us the return level from 20 years, 40 years, and all the way up to 100 years event. So when people are building bridge, they know what's coming to them.
This is the animation.
Yeah.
I guess it doesn't loop, it just loops.
It's pretty exciting.
That is exciting. Okay.
Yeah. So if we can do that, it's very similar if we were trying to do it for the non-stationary time series. We're just going to replace this into two parameters, and all this rest is the same. What the method we take is we first trying to fit it for the hobby airport, and we compute the parameter for each of them. Then we compute it for the rest of the 534 stations. So, and then we use the spatial smoothing and everything, which is pretty cool. And Doug helped us with that. And the challenge we faced at that stage is we kind of predicted for the ocean as well. We have to use the elevation map to get rid of the ocean. So it's one of the challenges. Yeah.
One thing that's actually really cool about this animation, as you see it's cycling through 20-year return level, 40, 60, 80, 100, is once we've fitted the distribution to the data, it's not very difficult at all to compute these quantile values. So we do the bulk of the hard work fitting into the distribution, doing the parameter tuning of what the scale, location, and shape parameters are. And then we have this fitted distribution, and you could hand that out to someone like an engineer who wants their structure to work for maybe 100 years, and they want to think about what the 100-year return level is. Maybe another engineer only wants their structure to last for 50 years. So they can use our fitted distribution and easily compute the 50-year return level.
So there are a few challenges and limitations of the model you should be aware of. First, data range is somewhat limited. We have data from 1949 to 2017, so 68 years. So that seems like a lot of data, but because we are essentially blocking it by year, we have 68 data points. And so when we are looking at 100-year return periods, we're essentially extrapolating a bit, and it becomes hard to isolate signal from noise. And the second thing is that we sort of have very few covariates in our model. Even as we were doing a non-stationary model, we assume that these parameters follow like a really simple linear time trend. So you have mu equals to mu0 plus mu1t. We've tried different models where we've taken sea surface temperature, interaction terms, sort of thing. But when we do likelihood tests, this model is still the best. For further research, we could make a model to forecast not just extreme values of rainfall, but just daily rainfall in general. And so when you can compare the results, it gives you some more information about that. Another assumption we made is that blocks are by the year, and so there might be some seasonality. We can account for that as well. Anything else?
Thanks to everyone that helped us out with the project. Thank you.
Any questions? Yeah.
Can you please repeat what equation did you use for covariance and what equations did you use for extrapolation equation?
Could you say again?
Can you please explain or rephrase which covariance function you used and how you interpolated data?
Okay. So this isn't a predictive model. We're fitting a distribution to like empirical data. Like the model is essentially like annual rainfall fits to this distribution. It's like an identity relationship.
I think the question is how you created the surfaces.
Oh, the surface, those surfaces.
Is that right?
Is that the surface? Okay. We use Doug's package that uses the thin plate spline. In general, we didn't really build a spatial model, and we weren't thinking much about actually doing a spatial analysis with that. The point of this graphic is to try to like send a clearer message with it. It would be more accurate to just show the individual values for the different stations, but we're trying to make it for you guys as the viewers that it's not as confusing that you need to look at all of these specific 535 points. You can just see in general places near Louisiana, southern Alabama, southern Mississippi have higher rainfall events.
You're not hoping to use this data to predict for future rainfall events so that companies could possibly use that?
That's the hope for future.
That would be future
Yeah, that would
research.
be- This would be the base for that.
So when we said return levels, you should interpret that as saying in the next 100 years we expect, the maximum rainfall in that period to be whatever we found. So it's not
Based on the distribution.
Right.
Not based on.
Anything else? All right, let's thank the team.